Welcome back to Ketone Body Metabolism on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to my channel for future videos and notifications. In this video, we're going to discuss the catabolic pathways for all three ketone bodies. And remember, in the previous video, we looked at the biosynthetic pathway, and I just want to remind you of a couple of things before we get going. Remember that the liver manufactures ketone bodies, and it does so in times of fasting. So when you haven't eaten, let's say, for about 7 or 8 hours, and your blood glucose levels have fallen substantially. So the body's forced to rely on fatty acids. And so these acetyl-CoA molecules, from which we make ketone bodies, these acetyl-CoA molecules come from fatty acids that are beta-oxidized in the liver, and then those acetyl-CoA molecules can then go and form ketone bodies. And these are the three ketone bodies: acetoacetate, beta-hydroxybutyrate, and acetone. And all three of these ketone bodies are dumped into the blood, and they travel to peripheral tissues such as the heart, skeletal muscle, the brain, the kidneys, and there's others. And those tissues take up the ketone bodies, and they're going to perform these pathways in this video for producing energy, and we'll see how that actually occurs. Now remember, the liver only makes the ketone bodies. The liver does not actually metabolize them. And there's a very important reason which we'll discuss here on this slide. And this slide is really just discussing acetoacetate and beta-hydroxybutyrate. These are from the liver, obviously. Here's the structure of beta-hydroxybutyrate, and here's acetoacetate. Now, in tissues such as the muscle or the brain or something like that, we do have this enzyme as well, beta-hydroxybutyrate dehydrogenase. Here it's going to perform the reverse reaction. It's going to convert beta-hydroxybutyrate back into acetoacetate, because really acetoacetate is the direct source of the energy. We have to first oxidize this hydroxyl group into a ketone, all right, before we can actually get any energy out of it. Now, if we just take in direct acetoacetate, this reaction is not necessary. It'll just be converted down here to acetyl-CoA. But like I mentioned, if we import directly beta-hydroxybutyrate, it has to first be oxidized into acetoacetate. And notice the nice thing here is, in the cell that's doing this, we actually get out an NADH right there. Now, this next reaction is extremely important to understand. So first of all, what does it do? It converts acetoacetate into acetoacetyl-CoA. So really what's happening here is this oxygen right here gets replaced with a CoA, and now we have something that we've seen before, acetoacetyl-CoA. All right. This enzyme is called beta-ketoacetyl-CoA transferase, and the CoA is actually going to come from succinyl-CoA. So we will have to pull that out of the Krebs cycle, but then again we get back a succinate, and that can go right back into the Krebs cycle and keep fueling it. Okay, so not really much is lost in that case. What's important about this enzyme beta-ketoacetyl-CoA transferase is this enzyme is not expressed in the liver. Okay? What would happen if the liver expressed this enzyme? Well, the liver obviously manufactures beta-hydroxybutyrate and acetoacetate. So if the liver had this enzyme, it would just convert all the acetoacetate to acetyl-CoA, and there wouldn't be anything good, right? You just consume the ketone bodies you just made in the same tissue, and there wouldn't be really any left to distribute to the rest of the body. So it makes sense that the liver does not express this enzyme. Okay? So the liver cannot catabolize acetoacetate or beta-hydroxybutyrate. But the peripheral tissue, such as the muscle, the brain, the kidney, etc., they do have this enzyme. And so they're going to be able to convert acetoacetate into acetyl-CoA, as I've just discussed. And then the acetoacetyl-CoA can be metabolized into 2 molecules of acetyl-CoA through the action of the enzyme thiolase, which pretty much is ubiquitously expressed in most tissues. All right? And this is important because what we now see is that in addition to getting out an NADH in the first step here from beta-hydroxybutyrate, these 2 ketone bodies will be metabolized to 2 molecules of acetyl-CoA. And these molecules can then go in and fuel the Krebs cycle. And obviously with the Krebs cycle per turn, we're going to get 3 NADH and 1 FADH2 and 1 ATP/GTP. So these are going to be used by those cells to produce energy. So hopefully this makes sense. This is how beta-hydroxybutyrate and acetoacetate generate energy in the form of these 2 molecules right here. And also, beta-ketoacetyl-CoA transferase is not expressed in the liver, so therefore the liver does not metabolize any of the acetoacetate that it makes. All right? Now, these pathways right here, or this pathway I should say, is very well characterized. This image is from Leninger's Principle of Biochemistry, and really you could find something like this in any biochemistry textbook you look in. It'll have this. Pretty much every biochemistry textbook, however, does not have acetone catabolism. All right, it does not have a pathway which degrades acetone. Now, in many books of antiquity, and this is kind of what I read, these are books that basically are not really as up to date, even if they're published very recently. They will all say that acetone is a metabolic end product, meaning it doesn't get degraded any further, and acetone really is just exhaled, and you would find some in the urine, but it's basically just gotten rid of, not through a metabolic pathway, just through exhalation or urination. This is not true completely. It is exhaled, and you can find some of it in the urine, but acetone is actually a major source of energy for cells. The reason why it's not included in most textbooks has to do with the fact that really to include something in a textbook, you have to have a lot of really, really good evidence for it. Really concrete evidence. So if you have a pathway in like glycolysis in a book, every enzyme in that pathway ought to be extremely well characterized. And obviously for glycolysis, all 10 of them are. Now, there is very good experimental evidence that acetone is catabolized to pyruvate in cells. This has been demonstrated experimentally many times. However, there's a couple enzymes in here that are not very well characterized, such as this one right here, and then also this one right here. The reason for that is beyond me. I don't know the exact reason why they're not really able to deal with those enzymes yet, but the fact is they're able to directly measure acetone conversion to pyruvate in cells. So this pathway does occur. All right. Now, acetone can be imported into a cell just as the other two ketone bodies, and it's first oxidized by a cytochrome P450 enzyme into this molecule called acetol. One of these carbons right here gets hydroxylated, basically. Okay, and this is actually a microsomal enzyme. It's a P450. It's the same enzyme that actually metabolizes ethanol in the microsomal pathway, CYP2E1. That's this P450. And it generates acetol. Now, acetol is going to be reduced, meaning this ketone right here is actually going to be reduced into an alcohol. Again, this enzyme is not completely characterized right here, but it's going to use reducing equivalents from NADH, and you're going to get this molecule 1,2-propanediol. All right. Then 1,2-propanediol is going to be reoxidized into this molecule called L-lactaldehyde. All right. And that's going to occur through oxidation. So the NADH we just used, we're going to get right back. This hydroxyl over here, rather, is going to be oxidized into an aldehyde, which we see right here, characteristic of L-lactaldehyde. And then L-lactaldehyde is going to be oxidized into a carboxylic acid over here. That's going to occur through the same enzyme that just did this. Okay, it's the same one here. And we now have L-lactate. Now, we know what L-lactate is. We know exactly what that is. It's just going to get now oxidized into pyruvate by lactate dehydrogenase. And this enzyme is known, okay? But this lactate is going to be converted into pyruvate by lactate dehydrogenase. And so ultimately what we see through this pathway is that we actually have a net generation of NADH. Yes, it's true we waste one in the first step, okay? We get it right back here for a net of 0. And then we actually get 2 out of it right here in the last 2 steps. So we generate 2 NADH, but also we generate pyruvate. And we know exactly what's going to happen to pyruvate. In cells that import the acetone, the pyruvate can be used to oxidize into acetyl-CoA. And that can also fuel the Krebs cycle, just as we saw for these other 2 ketone bodies. There is also some evidence that the liver can utilize this acetone. Okay, I know I said the liver doesn't utilize the ketone bodies, but it's not utilizing these 2 right here. Okay, and that's because the liver does not express this enzyme right here. However, there is some evidence to suggest that the acetone can be picked up by the liver, the same cell that made it, and then the acetone can be made into pyruvate, which is important because if you're in a state where you're producing ketone bodies, a fasting state, that's the same type of state where you'd also be doing gluconeogenesis. And so in the liver, this could be used to make gluconeogenesis. All right? So hopefully this video made sense to you, and now you understand a little bit more about ketone body metabolism and got some new good information here on acetone. Please make sure to like this video and subscribe to my channel for future videos and notifications. Thank you very much.